When we talk about artificial intelligence systems today, especially large language models, computer vision systems, recommendation engines, or scientific deep learning workloads, we quickly run into a fundamental reality: modern AI is as much a hardware story as it is a software story. You cannot meaningfully understand the capabilities, limitations, cost, and scaling behavior of AI without understanding hardware accelerators. So in this session, I want to walk you through AI hardware accelerators from first principles, in plain English, but at a level that respects a technically mature audience. Let's start with a basic question: why do we need hardware accelerators at all? Why are general-purpose CPUs not enough? A CPU, the central processing unit, is designed to be extremely flexible. It can run operating systems, databases, web servers, compilers, and arbitrary programs. It is optimized for low-latency execution of a wide variety of instructions, including branching logic, pointer chasing, and irregular memory access patterns. CPUs are very good at handling complex control flow and tasks where the instruction stream changes frequently. Deep learning workloads are different. Most of the computational cost of training or running a neural network comes from a very small set of mathematical operations, especially matrix multiplications, convolutions, vector additions, and nonlinear activation functions. If you look at a transformer model, the dominant operations are dense matrix multiplications in attention layers and feedforward layers. These are highly regular, highly parallel, and mathematically structured operations. CPUs can perform matrix multiplications, but they are not optimized for performing millions or billions of multiply accumulate operations in parallel. They have relatively few cores, and each core is optimized for sophisticated control flow rather than raw arithmetic throughput. So we need hardware that is optimized not for generality, but for throughput on specific numeric workloads. That is where hardware accelerators come in. The first mainstream accelerators for AI were graphics processing units, GPUs. Originally designed for rendering graphics in video games and 3D applications, GPUs were built to perform massive numbers of similar operations in parallel, such as shading pixels or transforming vertices. These operations map very well to linear algebra. Around the mid-2000s and early 2010s, researchers realized that GPUs could be used not only for graphics but also for general-purpose computation, particularly for workloads that are highly parallel and numerically heavy. A GPU differs from a CPU in architecture. Instead of a small number of complex cores, a GPU has thousands of simpler cores organized into streaming multiprocessors. The design philosophy is throughput over latency. If you have a large batch of similar operations, the GPU can distribute them across many cores and execute them concurrently. The cost is that individual threads are less powerful and branching is more expensive. But deep learning is dominated by large, regular numeric kernels, so this trade-off is ideal. The key hardware primitive in neural network computation is the multiply accumulate operation. If you compute a matrix multiplication, say multiplying matrix A by matrix B, each output element is the dot product of a row from A and a column from B. A dot product is a sequence of multiplications followed by additions. So if you want to accelerate deep learning, you want to maximize the number of multiply accumulate operations per second. GPUs are designed to achieve extremely high floating point operations per second, often measured in teraflops or petaflops for modern data center devices. Over time, GPU vendors added features specifically targeted at deep learning. For example, specialized tensor cores were introduced. Tensor cores are hardware units that perform small matrix multiplications in a single fused operation. Instead of performing scalar multiplications and additions one by one, a tensor core can multiply small matrices, such as 4 by 4 or 8 by 8 blocks, and accumulate the result in a highly optimized pipeline. This drastically increases throughput for deep learning workloads, especially when using lower precision arithmetic. This brings us to another crucial concept: numerical precision. Early scientific computing focused heavily on double precision, 64-bit floating point. Deep learning, however, is surprisingly tolerant to lower precision arithmetic. In many cases, 32-bit floating point, 16-bit floating point, or even 8-bit integer arithmetic is sufficient. Lower precision means fewer bits per number, which means less memory bandwidth and more arithmetic operations per unit area and power. Hardware accelerators take advantage of this tolerance by supporting mixed precision and reduced precision arithmetic. Precision is not just about storage. It directly affects energy consumption and throughput. A 16-bit multiply consumes significantly less energy and area than a 32-bit multiply. Therefore, if your model can be trained or inferred with 16-bit arithmetic, you effectively double your compute density, sometimes more. This is one reason why AI accelerators are tightly coupled with software frameworks that manage numerical scaling, loss scaling, and quantization techniques. While GPUs became the dominant platform for AI training and inference, they are not the only hardware accelerators. Companies began designing application-specific integrated circuits, or ASICs, specifically for AI workloads. An ASIC is a chip designed for a particular purpose, rather than for general computation. One prominent example is the Tensor Processing Unit, or TPU, developed by Google. TPUs are designed around the idea of systolic arrays. A systolic array is a grid of processing elements that pass data rhythmically through the array. Imagine a 2D grid where each cell performs a multiply accumulate operation and passes intermediate results to its neighbors. Data flows through the array in a highly structured way. This architecture is extremely efficient for matrix multiplication because it minimizes data movement and maximizes reuse of input values. Data movement is a central theme in hardware acceleration. In modern chips, moving data often costs more energy and time than performing arithmetic on it. Accessing off-chip memory, such as DRAM, is orders of magnitude more expensive than accessing on-chip registers. Therefore, hardware accelerators are designed to maximize data locality. They use large on-chip buffers, scratch pads, or caches to keep frequently used data close to the compute units. When you train a neural network, you repeatedly multiply weight matrices by input activations. If the weights are reused across many inputs in a batch, you want to load them once and reuse them as much as possible before evicting them from fast memory. Accelerator architectures are designed with these reuse patterns in mind. Systolic arrays are particularly good at keeping data in flight and reducing redundant memory accesses. Another dimension of accelerator design is parallelism. There are multiple types of parallelism in AI workloads. First, there is data parallelism, where you process different input samples in parallel. Second, there is model parallelism, where different parts of the model are distributed across different compute units. Third, there is pipeline parallelism, where different layers of a model are processed in a staged manner across devices. Hardware accelerators must support these forms of parallelism through high-bandwidth interconnects and scalable communication protocols. In a data center setting, a single accelerator is rarely sufficient for training state-of-the-art models. Instead, you have clusters of accelerators connected by high-speed networks. Within a server, accelerators are connected by high-bandwidth interconnects that allow them to share gradients and activations. Across servers, specialized networking hardware ensures low latency, high-throughput communication for distributed training. Communication overhead can become the bottleneck. When training large models with data parallelism, each device computes gradients on its mini-batch and then synchronizes those gradients with others. If the network is slow, the devices spend time waiting rather than computing. Therefore, accelerator systems are designed not only as chips but as integrated platforms that include compute, memory, and networking subsystems.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.